Recording and okay, hello everyone. Welcome to the seminar this week. It's our great pleasure to have Professor Kenichi Shimizu from Shibaura Institute of Technology to give the talk. Professor Shimizu has done very solid work in the theory in the development of theory of tensor categories and the related topics. So today he will talk about the rigidity of the category of local modules. Welcome.
Okay.
Please.
Yes. So thank you very much for introduction, and I also thank the organizer for this seminar for giving me to this opportunity to talk here. And okay, so this talk is based on these preprints, which was already available on arXiv. And Robert McLeay, a few weeks ago, he gave a talk on VOA in this seminar, and actually, so a part of his talk mentions this paper, this preprint, and I will give give emphasis on some category theoretical aspects, and of course, I will talk about some motivation from the VOA theory, but actually, so this talk will be a kind of a category theory talk. Anyway, so this is a plan of my talk. So first, I briefly recall some basic notions from algebraic objects in braided monoidal categories, namely the notion of algebra, the notion of commutative algebra, and module over them, and also introduce the notion of local modules, which is very important in the recent study of vertex operator algebras. And then this is actually a main results or main observation that states that under certain setting, the category of local modules has a nice closed monoidal structure. And as a corollary, we will have some criterion for the category of local module to be rigid. And as an application of this result, I will give some construction of non-semi-simple modular tensor categories, and then give some remarks. I'm sorry, so because of time restriction, I have removed this, but I'm sorry, it's still is a table of contents, but anyway. Okay, so throughout this talk, K is an algebraically closed field. And unless otherwise noted, vector space is assumed to be over K. Okay. So now I begin the main content of my talk. Okay, so in representation theory, we often have some procedure obtaining a new representation from two representations. Namely, in group theory, if we have two group representation, we will get a new group representation by taking its tensor product. And also the same situation appear in the context of CFT, conformal-field theory. But actually, the definition is quite difficult. Anyway, so some people in mathematical physics, they are interested in certain tensor product operation, which is actually called the fusion product for the representation of some vertex operator algebras. Anyway, so an abstraction of such a situation is called the monoidal category in the category theory. And roughly speaking, I think I can skip those slides, but anyway, so roughly speaking, a monoidal category is a category that is equipped with a certain binary operation, which denoted by the same symbol as the tensor product. And with respect to this operation, basically, the category is a kind of a monoid. So we call such a category monoidal category. And one often requires operation. This operation is commutative up to isomorphism. Namely, abstraction of such a setting is called a braided monoidal category. Namely, a braiding of a monoidal category is a natural isomorphism between x tensor y and y tensor x, and satisfying certain axioms called so-called hexagon axioms. And yes, so a braided monoidal category is a monoidal category equipped with such a structure. Okay. Now, Okay, so if you are really interested in some mathematical definition of such a notion, then you can construct this EGN book. And I think I will use this reference in many times in this talk. So anyway, so this is a basic framework for us. And once we have a monoidal category or a braided monoidal category, we can consider algebra in that category. Namely, let's see a monoidal category. Then an algebra in C is defined to be an object equipped with two morphism, namely which one called multiplication and one called unit, and satisfying the same axiom for associative unitary algebra. But of course, in the categorical settings, the notion of elements doesn't make sense. So we need to write the associative axiom by such a diagram like this. And we also need to write a unit axiom by the diagram like this. Anyway, so there is a notion of algebra, and now we can say whether algebra is commutative or not. And to discuss the commutativity of algebra, we actually need a braiding, namely an isomorphism between x tensor y and y tensor x. And then an algebra A in C is said to be braided commutative if this diagram is commutative. So for example, if C is a category of vector spaces, then this braiding, the usual braiding is given by just a flip of tensor product components. And actually, this notion coincides with the usual notion of commutative algebras. But the point is that this map may not be a kind of trivial one. So even for the case where C is a category of supervector spaces, then we will have a non-trivial braiding, which is usually called a supersymmetry. And then in that setting, braided commutative algebra is usually called a supercommutative algebra or something like that. Anyway, so we can the point is that we can consider the commutative algebra in a braided monoidal category. Okay, now like the case of ordinary rings, given an algebra, we can consider a left module or right module. And the definition of a left module is not so difficult. So if we have if we have an algebra A in the category C, in the monoidal category C, then left A module is just an object equipped with such a morphism that is associative and unitary in a certain sense. In a sense, such like the associativity of unitarity of an algebra. And in a completely analogous way, we can define right modules and bimodules. And under some technical assumptions, the category of bimodules has a monoidal structure by the tensor product over the algebra. Okay, this is a very well-known theorem. And suppose that the monoidal category admits coequalizers and the tensor product preserves them. So if you are not familiar with some such abstract setting, you may consider the case where C is an abelian category and the tensor product operation is right exact. And in that case, yes, our assumption will be automatically satisfied. Anyway, so once we have such a setting, then the category ACA of A bimodules, this is a monoidal category with respect to the tensor product over A. But of course, we need to define the tensor product over A without mentioning the notion, without mentioning elements of the object. Actually, in terms of the category theory, we can define the tensor product over A like this. So namely, the tensor product over A for two bimodules is just a coequalizer. So you may think as a this is a maximal quotient of this object, where this map and this map will be equal. And if we write down this notion in the case where C is a category vector space, you will have a completely same definition as a category, as a tensor product over the ring. So actually, this is a, how to say, this is a natural extension of such a notion to the setting of monoidal categories. Anyway, the fact is that under some nice assumption, the category ACA of A bimodules is a monoidal category. So we have actually, we actually have a new monoidal category from algebra in a monoidal category. Okay, now we talk about the main player of this talk. That is a category of local modules. Okay, the setting is as follows. C is a braided monoidal category with coequalizers, and the tensor product preserves them. Okay, so again, okay, so please remember that this is not so rare case. Namely, you may assume that C is a abelian category and the tensor product is right exact. That's enough for guarantee this setting. Okay, now suppose we also have a commutative algebra in the braided monoidal category C. Then the right A module can be A by module by defining the left action in this way. Okay, so if we want to define a left action, so we want to have a morphism from A tensor M to M. Okay, now suppose we have a right action of A. So then we first flip the order of tensor product by using the braiding, and then we apply the right action. And then actually, by this left action, actually, so M is actually a bimodule of in the category C. And actually, we can show that the category C of right A modules in C is actually a monoidal full subcategory of the category of A bimodules. And it is well known that the category of right modules over commutative ring is a monoidal category with respect to a tensor product over R. Unfortunately, this is not true for CA in general. Okay. Namely, and to get the braided monoidal category, Pareigis introduced this notion. So, right A module is said to be local if this equation holds. Okay, so we have used the braiding to define a left action, but there is no reason why we use this braiding. Namely, the braiding. There are two notions of there are two kinds of braiding, namely the positive braiding and the negative braiding. And okay, so at this point, we have used the braiding positive crossing to define a left action on the right A module. However, we can define the negative crossing to define a left action on this object. And if these two actions coincide, then we say that it is a local module. Okay. And the famous result of Pareigis is that the category CA local of local modules is actually a braided monoidal category. Okay, so actually, and this is very old result. And okay, so now I should explain why we are interested in this notion. Actually, at the time Pareigis found this theorem, we don't. I think no one think this can be applied. This notion have some application to the context of conformal field theory or something, some related topics. But actually, so recently we are interested in this category from the viewpoint of conformal field theory. Okay, so actually I'm a beginner on VO theories, but I can say something about something about the motivation why we are studying the category local modules. Okay, so let V be a vertex operators algebra, and then under suitable assumption, the category of V, the category left V of representation V has a structure of a braided monoidal category, and there is such a picture established by many authors. And okay, so first of all, suppose we have an extension of the vertex operator V, say W. Then it corresponds to a commutative algebra in the category of representation V. Okay, now one might ask, what is the representation category of W, the bigger BOA? Actually, it is equivalent to the category of local modules, where A is W, regarded as an algebra in the category C of representation V. So actually, this kind of correspondence has been established by many authors, and I think the first paper should be the paper of Kirillov and Ostrich, and they mention the case where everything is semi-simple, and then it was the theory was the tensor product theory was extended to the very general setting by Juan Kirillov and Lepovsky, and now there is a nice survey and many nice exposition given by Kraitzhi, Kanade, and Maclay. Anyway, so we have established notion of this, and because of this, we can ask this question: under what condition for C and A does C local have a nice property? Okay, so from the BOA perspective, this question has this meaning. So if we have a small BOA, and suppose we have a large BOA that extends B, and we want to know some representation theoretic property of the bigger BOA, and it corresponds to this question. And what condition for C and A does representation category of the bigger BOA have a nice property. And of course, nice property depends on what you are interested in. But here I will mention as a nice property, so abelian, semi-simple, rigid pivotal ribbon, or Grothendieck failure. So anyway, so the question is, under what conditions for C and A does C local have a nice property? And today I will not mention, but actually the converse question is also important. Namely, under what condition for C, A, and C local does C have a nice property? Okay, so this is actually really difficult problem. But this aims to consider as follows. So suppose we have a big VOA, say W, and we have a sub VOA V, and we want to know representation theory of V from the representation theory of W and some additional information. Actually, under some setting, CA local is equivalent. Okay, so suppose W is a, say, homomorphic VOA, then the category CA local is actually under this setting, this category is equivalent to the category of vector spaces, which has from the category theoretical perspective, which has no information. But so because of this, we need to impose many assumptions to solve this question. And actually, this will be a very nice research area, but I have no idea for I have no nice idea for solving attacking this question. So anyway, so today I mentioned this question: under what condition for C and A does C local have a nice property? And one result is that under certain nice assumption, C local is actually rigid monoidal category. Okay, now I'm going to introduce a basic framework for dealing with this question. Okay, that is a so-called closed monoidal category. Okay, so this is at least well known for category theorists. Anyway, so a monoidal category is said to be left closed if this functor, identity tensor X, has a right adjoint for all object X. And the right adjoint of identity tensor X is written as this symbol. And so totally speaking, we will have such a natural isomorphism. Okay. And okay. And similarly, we say that C is right closed if we have such a nice isomorphism. And in general, left internal Hom functor and right internal functor are different. But anyway, so we say that C is left closed if there is such an isomorphism, and right closed in okay, so anyway, so this is a definition of left closed, right closed monoidal category, and we say that monoidal category is closed if it is left and right closed. Okay. Okay, now I want to emphasize that this setting is appear in many places of mathematics, and the first easy example is this. the category of sets, it is a monoidal category with respect to the product, just a product of sets. Then in this case, the internal Hom factor is given by all maps from X to Y. Okay. And also bimodule over ring forms a closed monoidal category. In this case, the internal Hom factor is given by some homomorphism from X to Y, but only considered one side, how to say. So because X and Y are bimodules in this context, we can consider the space of left R linear morphism and right R linear morphism, etc. And one side gives one side of internal Hom factor. Okay, now we consider the category of left modules over bialgebra. Actually, so in this case, the category also has a closed monoidal structure. In this case, the internal Hom factor is a bit funny, and actually it is given by this formula. Here, H tensor X is a vector space H tensor X with a diagonal action, and we can show that this is actually a internal Hom factor for the category of modules over bialgebra. Okay, so if H is a Hop algebra, then H tensor X is isomorphic to a free module over H with basis X. Slightly anyway. So H tensor X with left H modular structure only here, and by using this observation, we can show that if H is a Hop algebra, then the internal Hom factor is given by this very how to say simple formula. Okay. Anyway, so I wanted to emphasize there are plenty of examples of closed monoidal category. Okay, in a closed monoidal category, okay, so I want to explain what a rigid monoidal category from a viewpoint of the closed monoidal category. In a closed monoidal category, there is a canonical morphism from here to here, from here to here. Okay. Naively speaking, this is a map, something like this. But of course, in the setting of category theory, there is no notion of element. So we need to establish such a morphism by using some unit and co-unit of the adjunction. But anyway, so we can establish an analog of this map in the context of monoidal category. And actually, rigid monoidal category can be defined as follows. An object is said to be left rigid if this morphism is invertible for any object Y. And if this is the case, this object is called a left dual object. And the co-evaluation map is given by this composition. Okay, and right rigidity is defined analogously by using the right internal Hom factor. And the rigid monoidal category can be defined as a closed monoidal category where every object is left and right rigid in this sense. And yes, so one may notice that this definition looks different from some popular definition written in literature. However, you can check that this is indeed agrees with a popular one found in the, for example, in the textbook of EGNO. So today I want to deal with rigid monoidal category as a subclass of closed monoidal category. So we adopt this. I adopt this definition. And okay, so this is a very small remark. Why I call one-sided dual as a left rigid and another side dual as a right rigid. Because the reason is this: in the category of end factors, a left dual object is a left adjoint factor. So this is why I adopt this left and right convention. But please remark that some authors have different conventions. So some author call my left rigid object right rigid object. So there is still some confusion. But anyway, so the reason this is the reason why I adopt this convention. Okay. Okay. So now I want to give one remark which will be important in my theory. Okay, so first of all, a full subcategory of closed monoidal category may not be closed, unfortunately. And the point is that even if a full subcategory is closed monoidal category, it may not share the internal form factor with the ambient category. Okay, here this is an example. The category of H comodules for H is a bialgebra is actually a closed monoidal category. I'm not sure this is clearly written in literature, but you can prove this by using the adjoint functor theorem. Anyway, so the fact is that the category of H comodules is a closed monoidal category. Okay, we now consider two closed monoidal category. One is a category of Z-graded vector spaces, which can be identified with the category of comodules over the group algebra of the set of the group of integers. And we can also consider the category of Z, how to pronounce this? Anyway, so the category of vector spaces graded by non-negative integers. And this is also a closed monoidal category because this can be identified with the comodules over the monoid algebra of the group of monoid of non-negative integers. Okay, now we observe there is this isomorphism. Hom C x tensor K1 from K0 is isomorphic to Hom C x K-1. Okay, so because of this tensor factor, the grading of X shift up, down. It's difficult to explain, but anyway, so so this tweaks the grading of this. So because of this, the zero graded subspace of these is equivalent to the -1 graded part of X. So we have this isomorphism. This means that so when we consider internal form factor in the category C, this internal form object is isomorphic to K-1, which is not an object of the category D. So please remember that the category D is it is a category of vector spaces graded by non-negative integers. And so if X is graded by non-negative integer, this vector space is 0. So we see that this is actually 0 in the category D. So this is an example that I mentioned this. So even if a full subcategory is a closed monoidal category, it may not share the internal form factor with the ambient category. So so we need to check how to say. So anyway, so this is a kind of starting point of my theory. Now I mentioned the closed monoidal structure of the category bimodules. Now suppose C satisfies certain technical condition. Namely, C is a closed monoidal category with equalizers and coequalizer. And actually, so so to guarantee that this condition is satisfied, it's sufficient to assume that C is an abelian monoidal category. And anyway, so we also assume that A is an algebra in the category C. And then we can define the kind of internal tensor product by this, induced by this natural transformation. So anyway, so we want to formalize this kind of map in the context of monoidal categories. And we can do by using the natural transformation and using the Yoneda lemma, we will get kind of this natural transformation. Now by using this natural transformation, I define this object, Hom A X L Y, this object. And actually, the category of the category ACA of A bimodules is a closed monoidal category with left internal form factor given by this formula. So actually, this is a abstraction of the set of right A module maps from X to Y. But again, I want to emphasize that there is no notion of elements in the setting of category theory. So we need to use some categorical technique to formulate what is a set of right A module maps from X to Y. And actually, this is one answer, namely. So equalizer is you may think equalizer as a kind of sub-object of this object, and where this is a sub-object, where this map and this map will be equal. And actually, so by using this technique, we can explicitly construct the internal form factor on the category of A bimodules. And by switching the left and right, we will have a right monoidal, right internal form factor for this category. Okay. Anyway, so the point is that we can write down the internal form factor for the category of bimodules in a somewhat explicit way. This is the point for my talk. Okay, now we introduce a somewhat technical notion. How to say? This is actually very essential for studying the monoidal category. But anyway, so at this point, I just introduced this definition just by saying something. Anyway, so the Dreyfus center, maybe all of you know, it is a braided monoidal category whose object is a pair of x and sigma, where x is an object, and sigma is a so-called half braiding, which satisfies half of the action of the braiding. Anyway, so we consider this category, and we now actually, so the Dreyfus center is a braided monoidal category. So we can consider the notion of a commutative algebra in the Dreyfus center. Okay, so suppose we have a commutative algebra in the Dreyfus center, and then we define CA sigma to be the full subcategory of category of A bimodules that satisfy this condition. Namely, okay, so because X is a bimodule, we have left action and right action. And this equation says that the left action, say, is given by right action composed with the braiding. Okay, so this is actually what is. This is actually this is what I want to mean in this equation. And anyway, so by using by defining CA sigma as follows, we can show that CA sigma is actually a tensor monoidal full subcategory in the sense that it is closed under the tensor product over A. Okay, this is a most important observation. Okay, so as I said, even if full subcategory is a closed monoidal category, it may not share the internal form factor with the ambient category. However, it shares the internal form factor in this setting. Namely, if X and Y are objects of CA sigma, then their internal form factor actually belong to the same category. And this means that CA sigma is a closed monoidal category. But this lemma says more. CA sigma is a closed monoidal category in such a way that its internal form factor is same as the bigger category. This is a very important point for this theory. Okay, now I want to explain how to apply this lemma to get some nice theorem for the rigidity of some category. Okay, we consider this setting. C is a closed monoidal category with equalizers and coequalizer. And let A be a commutative algebra in ZC such that this category is rigid. Okay, now we assume that the bigger category is rigid. Actually, when the rigidity of ACA holds is a very difficult question, and I will discuss it in later. But okay, so from now on, we assume that the category ACA is a rigid monoidal category. And in this case, we can show that CA sigma, the category just defined is actually a rigid monoidal category. Okay, so the proof is now very easy. By the assumption, every object has a left dual object in the bigger category ACA. And we want to show that this belongs to the category, a smaller category CA sigma. But we have proved it already. Since this object belongs to CA sigma by the previous theorem, we can conclude that this is actually left rigid. And the right rigidity is proved in the same way. So once we assume that the bigger category is rigid, we can show that small category CA sigma is rigid monoidal. And actually, we can apply this method to the category local modules. Okay, so assume that C has a braiding C. Then we can define C, the category of local modules over A, over commutative algebra A. And actually, it is defined to be the intersection of CA sigma plus and CA sigma minus, where sigma plus is just a braiding and sigma minus is an inverse braiding. And the theorem is that CA local is braided rigid monoidal because this is closed under duality, and this is also closed under duality, and its intersection is also closed under the duality. So we can conclude that CA sigma is actually a braided rigid monoidal category. Of course, under the assumption that the category of bimodule is a rigid monoidal category. So anyway, so this is a very powerful tool for showing some category is a rigid monoidal category. And I wondered whether I should talk with this setting, but okay. So actually, so I wanted to concentrate on rigidity, but actually this setting is also important in recent study of vertex operator algebra. So I briefly mentioned this setting, namely the Grothendieck-Felder category. So it is introduced by Boyachenko and Drinfeld, and it is a monoidal category equipped with a certain object, which is called a dualizing object, satisfying this condition. So first of all, this functor is representative, and let dx be the representing object. Namely, suppose that we have this kind of natural isomorphism, and we can extend this assignment to an contravariant functor. And we say that C is a Grothendieck-Felder category if this assignment is an anti-auto equivalence on the category C. Actually, this is a strictly weaker notion than rigid monoidal category. But actually, from the recent study of vertex operator algebras, actually, this setting is very natural for representation theory of vertex operator algebra. So, so we are interested in this setting, and this is some remark. And one important remark for us is this. Actually, Grothendieck-Felder category is a closed monoidal category, and the closed monoidal structure can be written in terms of D, the functor D, in this way. So we may say that a Grothendieck-Felder category can be defined as a closed monoidal category satisfying some nice condition. So now we can situate a GB category in the framework of closed monoidal category, and then there is a chance that we can apply our result to GB category. Okay, so this is what this is. Okay. So suppose that C is a closed monoidal category with equalizers and coequalizer. Okay, so I will not talk about the detail, but this lemma says that under some assumption, we can show that the category CA sigma is also a GB monoidal category. And by the same way, we can also show that the category CA local is also a Grothendieck-Felder category. So I'm sorry, because of the time restriction, I will not talk about the detail, but we can prove this. And similarly, okay, so this is a strategy. Okay, so namely, show that the category bimodule is a GB category, and then check if the dualizing object belongs to the smaller category or not. And by this strategy, we have proved this kind of theorem. Okay, so this is a slight variant customized for application to the category local modules. And let's see, be a braided Grothendieck-Felder category with satisfying some technical assumption, and let A be a commutative algebra in this category. And then we can show that the category right A modules is a GB category with dualizing object. So we just need to consider whether this object belongs to this, and we can show that in this under this setting. And if moreover C has a ribbon GB structure, and if the twist satisfies some technical condition, then we can show that the category CA local is also a braided GB monoidal category. So So please look the detail in our preprint. But anyway, so I want to emphasize our results can be applied even for Grothendieck field setting. Okay. Okay. Now I want to talk about the main application of our result to the braided finite tensor category. I think this is recently much common, so maybe I can skip this. But anyway, so let me recall some basic definition. So first of all, finite abelian category is a linear category that is equivalent to the category of finite dimension left modules over finite dimension algebra. Okay, so namely, this is a very small abelian category. Anyway, but even if it's small, finite dimensional algebra is of course very difficult. So anyway, so finite abelian category is not so easy object. And a finite tensor category is, roughly speaking, it is a rigid monoidal category such that that is also a finite abelian category. And strictly speaking, we need to assume that the tensor product functor is bilinear, and the unit object is also the unit object is actually a simple object. Okay, and if we have a finite tensor category, then we can define its module over, like the case of module over ring. Namely, a finite left C module category, a finite abelian category, together with a certain functor from C times M to M, C times M to M, that is linear and right exact in each variable. And of course, by C module structure, I mean that this functor is associative and unitary up to isomorphism in a certain sense. Okay. And yes, again, you should consult the EGNO textbook if you're really interested in the detail of this definition. Okay. And for example, fusion category is just a semi-simple finite tensor category. And next important class of example is this, rep H, namely the category of representation of H, where H is a finite dimensional Kaji-Hopper algebra, is a finite tensor category. So anyway, so there are, even if we restrict the finite setting, but there still have so many examples. Okay. Okay, now I want to talk about indecomposable exact algebras. But because of time restriction, so I first talk about why I want to mention exact left comodular algebra. Okay, in my theory, the condition that the category of A bimodule is rigid is very important. So we want to know when this category is a finite tensor category. Okay, given the algebra A in the finite tensor category C, then we can consider monoidal category ACA. But in general, this is not rigid. So we want to know when this is a rigid monoidal category. And more strongly, we want to know when ACA is a finite tensor category. Actually, that property can be written as follows. So ACA is a finite tensor category if and only if A is indecomposable and exact. Here, indecomposable means that it cannot be decomposed into some product, a direct sum of ideals. And yes, so exact means the category of right A modules, which has a natural structure of a finite left C module category, is exact module category in the sense of Ettinghoff and Ostrich. Okay, so let me skip the detail of the definition, but anyway, this is known. And one more important is from the recent study of Ettinghoff and Ostrich, this condition, namely indecomposable exact, is equivalent to that A is simple and it satisfies certain technical condition. And Ettinghoff and Ostrich also conjecture that this is a finite tensor category if and only if A is just a simple algebra. And they have verified this conjecture for when C is rep H for some finite dimensional Kaji-Hopper algebra. So basically speaking, if A is a simple algebra, then this is a finite tensor category. But of course, the conjecture is not yet proved in the general setting, but you may think this condition is very near to the setting where A is a simple algebra. Okay. And actually, under some setting, we can show that the simplicity of A implies this. So simplicity is relatively easier to check. So we love this replacement of this condition. Okay, now I want to introduce the main the class of tensor category, which we are really interested in. That is called the modular tensor category. Okay, so for braided finite tensor category, its mu center is defined as follows. Namely, the object T that is satisfies this condition is identity equal to identity. So namely, we can consider double braiding. And if the double braiding untangle, we say that. And the set of all such objects is called the mu center of the category C. And we say that the braided finite tensor category is non-degenerate if the mu center is trivial, meaning that if the mu center is equivalent to the category vector spaces. And modular tensor category is a non-degenerate braided finite tensor category with a ribbon structure. Okay. And okay, so the above definition actually agrees with Lyubashenko's definition. And the modularity of a semi-simple ribbon finite tensor category is equivalent to the well-known definition for the invertibility of the S matrix. So actually, we are considering some kind of non-semi-simple modular tensor category in this setting. Okay, so by modular tensor category, many people talk about a semi-simple tensor category satisfying some condition. But for me, modular tensor category is not necessarily semi-simple, and I'm going to consider a non-semi-simple modular tensor category. And okay, so apart from the semi-simple case, there are plenty of examples. And the first example, of course, given by Lyubashenko, and he showed that under certain assumption on the order of Q, the category rep UQG of the representation of a small quantum group is actually a modular tensor category. And also we have this example. The Drinfeld center of a finite tensor category is actually a non-degenerate braided finite tensor category. And if it has a ribbon structure, then it is actually a modular tensor category. And this is my paper, but a criterion when the Drinfeld center is ribbon is already known by extending the known result of Hopf algebra given by Kaufman and Rutherford. So actually, from this construction, we will have a non-trivial modular tensor category by taking the Drinfeld center. Okay. Okay, let me give a main construction. For while we don't mention the ribbon structure, I will mention the ribbon structure in later. Namely, we will concentrate on the non-degenerate braided finite tensor category, which may not have ribbon structure. And this is a main result. Okay, so let C be a finite tensor category and let A be an indecomposable exact algebra in the category C. Then we have, okay, if A is a commutative algebra in the Drinfeld center, then this is actually a finite tensor category. Okay. And if C is braided and A is a commutative algebra in C, then we can consider the braided tensor category, braided monoidal category of local A modules. Actually, this is a braided finite tensor category. And now, suppose moreover that C is a non-degenerate braided finite tensor category, and A is a commutative algebra in C. Then actually, the category of local A modules is a non-degenerate braided finite tensor category. And today, I didn't explain, but for a finite tensor category, we can define a kind of dimension, which is called the Frobenius-Perron dimension. And the Frobenius-Perron dimension of this category is given by this formula. And this means that because Frobenius-Perron dimension is an algebraic integer, so this must be an algebraic integer. So this gives a strong restriction on such an algebra in a non-degenerate braided finite tensor category. Actually, this kind of phenomena has already known for semi-simple case, I think. And anyway, so we have established such a result in the non-semi-simple setting. Okay, so let me mention the difference between previous work. In previous works by Kirillov and Ostrich or Lowitz and Walton, A is assumed to be at least a separable algebra. and the coevaluation morphism was explicitly constructed by using the separability idempotent. In our setting, we don't assume that A is separable. Namely, the assumption of A is very weak than the previous works. However, instead of this, we don't construct dual object explicitly. Namely, we just show that there exists a dual object. And because of this, we don't know what the coevaluation morphism is. But anyway, so we have proved that rigidity in an abstract way by using our results. Actually, the claim 1, the claim 2 are direct consequence of our result on the rigidity. Namely, I have explained under certain setting, we can show that CA sigma and CA local are rigid monoidal category. And just by checking the assumption, we will get 1 and 2. The third point is a bit difficult. Namely, non-degeneracy is not so trivial. But actually, in this case, we can follow the basically same line as the previous works to show that C is non-degenerate. This is a detail, but okay, so because of the time restriction, let me skip these slides. So if you're interested in, please look our preprint. Anyway, so we can show that by using some previous results on the category theory, we can show that under some setting, CA local is a non-degenerate braided finite tensor category. Okay, now we want to know when CA local is a modular tensor category, namely when CA local has a ribbon structure. Actually, we also have an answer to that question. Okay, so, but assumption is a bit technical. So first of all, the notion of Frobenius algebra in a rigid monoidal category has been well established. And there is also a notion of symmetric Frobenius algebra in a pivotal monoidal category. And what we have proved is, let C be a modular tensor category with ribbon structure theta, and let A be a simple commutative symmetric Frobenius algebra in C. Then the category of local A modules is also a modular tensor category with the same ribbon structure as C. Okay, so this is a sketch of proof. So first, since A is a Frobenius algebra, the mysterious condition by Ettinghoff and Ostrich is actually satisfied. We can check this. And actually, we already assume that A is simple. So by the result of Ettinghoff and Ostrich, we can say that A is indecomposable and exact. So we can apply the previous theorem to our setting, to this setting. So because of this, we can show that CA local is actually a non-degenerate braided finite tensor category. So now we want to show that it has actually a ribbon structure. This part is a bit technical. So we can define the Nakayama automorphism for any Frobenius algebra, and actually it is equal to theta A since A is a commutative algebra. So Nakayama automorphism is kind of Nakayama automorphism is defined by kind of like this, something like this. So I'm sorry, it's difficult to explain such a small number. Anyway, so we can define the Nakayama automorphism for Frobenius algebra, and we can show that Nakayama automorphism equal to theta A, since A is a commutative algebra. But since A is assumed to be symmetric Frobenius, which means that Nakayama automorphism identity, theta A is identity. So this is just a computation by computation of Nakayama automorphism. And once we have computed, it directly follows from this equation. And by using this equation and some technical assumption, we can show that theta actually induces a natural transformation on the identity functor of CA local. And actually, we still have some technical discussion, but you can show that CA local. We can show that CA local has a ribbon structure induced by C, and after some technical computation. Okay, so there is a bit difficult question on the compass, and I'm sorry, let me skip this. But there's a very we have did some technical discussion when the compass holds or not. Okay. Okay, so finally, I want to talk about the Witt equivalence for braided non-degenerate finite tensor category. Okay, so for semi-simple finite tensor category, namely for fusion category, such a Witt equivalence is has been already established and studied so much. And okay, so like the case of non-semi-simple case, I'm sorry, like the case of mimicking the case of semi-simple case, we define the Witt equivalence for two braided finite tensor category as follows. I'm sorry, this should be non-degenerate braided finite tensor category. I'm sorry. So anyway, so we say that two non-degenerate braided finite tensor category C and D are Witt equivalent if there are finite tensor category A and B such that the Doreen tensor product of C and ZA and Doreen tensor product of D and ZB are equivalent as braided finite tensor category. Okay. And we have proved something about Witt equivalence by using some construction of non-degenerate braided finite tensor category. So first of all, the set of Witt equivalence classes of non-degenerate braided finite tensor category is an abelian group and as a binary operation given by Doreen tensor product. And actually the inverse is given by this formula. Actually, so this follows the reason why this is an inverse is if C is a non-degenerate braided finite tensor category, then there is such an equivalence. C tensor C bar is equivalent to the Drinfeld double of C, provided that C is a non-degenerate braided finite tensor category. Actually, so this is well known for semi-simple case, and non-semi-simple case, we need to use my characterization of non-degenerate braided finite tensor category and with some previous results by Ettinghoff-Nix and Osterich. Anyway, so because of these, we can say that we obtain the group of Witt equivalence classes of non-degenerate braided finite tensor categories. And let us call this the Witt group. Actually, this depends on the base field. So this is a Witt group over K. Witt group of non-degenerate braided finite tensor over K. Okay. And okay, now we can we want to know when an element of this group is an identity. Actually, an element represented by C is an identity element in the Witt group if and only if C is ZA for some finite tensor category C. And this is completely same result as a finite semi-simple case. And the third one is also important. Okay, so for non-degenerate braided finite tensor category C and D, the following assertions are equivalent. So first assertion is C and D are Witt equivalent. And actually, this is equivalent to that C times D, C tensor D bar is equivalent to ZA for some finite tensor category A. And the third point is also important. There are non-degenerate braided finite tensor category E and an indecomposable exact commutative algebra A and B in C, E, such that C is category of local modules over A in E, and D is category of local B modules in B. Okay, the third condition, okay, so this, okay, let us briefly discuss what this means. Anyway, this condition says that the Witt equivalent is generated by this relation. Okay, this generated by local module construction. So because we have generalized to the local module construction of non-degenerate braided finite tensor category to a very general setting, we can show that Witt equivalence is actually generated by the local module construction. So by the previous results, the local module construction is slightly restricted. So we cannot prove the third one under that setting. But actually, because we have generalized local module construction, then we get this result. Okay, this is some remark. And okay, so because I have no time, so let me give some questions. So the Witt group was originally considered for semi-simple modular tensor category. And we don't know whether semi-simple Witt group and non-semi-simple Witt group are different or not. We don't know. And is there a, so because of this, we may ask that, is there a non-semi-simple, non-degenerate braided finite tensor category that is not Witt equivalent to a semi-simple one? We don't know the answer. And actually, the famous non-semi-simple example, rep UQG, is actually Witt equivalent to a semi-simple modular tensor category by some results that this category can be constructed by a relative center construction. So unfortunately, we don't know non-degenerate braided finite tensor category that is really non-semi-simple in the sense that it is not Witt equivalent to a semi-simple one. Anyway. Okay, so this is a summary of my talk. And okay, thank you. Thank you for listening. Thank you for listening. I stop here.
Thank you very much, Kenichi, for the